Hello again, guys. Topic 2 notes. We're looking at electrons this time. We're going to look at writing a ground state electron configuration and drawing an orbital diagram for elements 1 through 18. If you are looking at going towards exceeding and the should and aspire to topics, you will then go to elements greater than 18, but 18 is our threshold for our expected level. So yesterday or the day before, whenever you worked on the Hopeful activity for this, you looked at how electrons were arranged in houses or like rooms to demonstrate these orbitals. And so we're going to talk about the three things that you ended that poll looking at, which was the Aufbau principle, Hund's rule, and the Pauli exclusion principle. So the Aufbau principle is build up. So similar to a building, you must build the first floor before building the second and third floors. So in the Aufbau principle, we must put electrons in the first energy level before filling up the second energy level. And the big number, remember, designates which energy level you're in. Hund's rule states that we cannot put two electrons in the same orbital within a sublevel before we fill each individual orbital with one electron first. So we see that these first two are examples of correct electron configuration orbital diagrams, and the bottom two are incorrect. Hund's rule is being violated in this bottom example here because we have the two electrons in the same orbital instead of separating them into two separate orbitals. So again, we're going to fill each individual orbital before filling or doubling them up. The example in the Poval activity with this was the bunk beds. So you're going to put one person in each bunk bed before doubling up people in bunk beds within the same room. Pauli exclusion principle then is the stating of that the two electrons cannot have the same spin within an orbital. And so the example of this being, it's not really shown that there's two electrons with the same spin. So like if this arrow was pointing up and this arrow was pointing up, that would be incorrect. But another way that you can do this incorrectly is by having the two that are by themselves in opposite directions. So they're going to fill in the same direction. So notice these two are down and these two are up. That's really the only difference between these two. They're both okay, but it's not okay to do them in opposite directions. And also it's not okay to have two arrows in the same box in the same direction. Valence electrons are those outermost electrons. We can tell and see where our valence electrons are by looking at electron configurations or orbital diagrams. So we're looking at the electrons that are in the highest energy level. So in these examples here, 2, our energy level 2 is the highest. 1 would be within or inside. 2 is going to be my outermost energy level. And so I'm going to add all the electrons that are in a energy level that has a 2. So I have 2 electrons here and 2 electrons here. So I would have 4 valence electrons in this electron configuration. Valence electrons are what are going to be doing the chemical bonding and the reacting that we will talk about in further topics, and they're really important as to the chemical properties of various elements and compounds, which we'll talk about in the future as well. So let's practice this. Oxygen has 8 electrons. There's a typo there, it says electros, hilarious. It has 8 electrons. We know it has 8 because there's no charge, and if we go to the periodic table, which is loading, there we go. Oxygen is number 8, which has 8 protons. So I represent the electron configuration starting with that 1s energy level, fill it up, 2s, fill it up, and then 2p, I have the 4 leftover electrons. There are 6 electrons that can go in the p, so I still have some space. Orbital diagram, again, I'm building up. So I'm starting at that 1s, I'm going to 2s, and then I'm filling my 4 electrons individually before doubling up. So I only have one orbital that has 2 electrons and 2 orbitals that have 1. Next up, we have fluorine. Again, we have a neutral fluorine. There's no charge here, so if we have 9 electrons, we have 9 protons. Electron configuration is going to be the exact same, except for now I have 1 more electron than I did in the oxygen. Same thing with the orbital diagram. It's going to look exactly the same, except for I have 1 more electron being represented. Next up, we have neon. Neon has 10, so we need to represent our 10 electrons. This is a noble gas. Noble gases are found in that far right column on the periodic table. They have a full valence shell, and that is what makes them non-reactive and makes them noble, or what we call noble. And so notice that all their boxes are full. Okay, it doesn't go up to the 3 or the 4 or the 5 energy levels, but its 2 energy levels are full. How many valence electrons does neon have? Well, you still look at that highest energy level, and we have 2, 4, 6, 8. With 8 valence electrons, its outer energy level is full. So another way that you can look at this is imagining this sitting on top of the periodic table that you have in front of you. And the metals off to the far left are going to be that S. Those are those sunny rooms. There are 2 elements, those 2 electrons that can be represented in that room, or those 2 people. and then the P being the nonmetals off to the right side of the periodic table. And these are going to have 6 boxes, which represent those 6 electrons. The periodic table is a great map. We'll continue to use it in our next topic as well to help us map this out. But I like this visualization of where those electrons are coming from, and if this helps you out, maybe jot it down on your notes. So a little I do section, I'm going to go through and do these with you. Aluminum, if we go to the periodic table, has no charge, so the number of protons in aluminum are going to equal the electrons. We have 13. So I need to represent 13 electrons with my electron configuration. I start with my 1s, I follow my pattern of 2s, 2p, 3s, 3p, and make sure that my electrons add up to the correct amount. I think this is the easiest way when I give you an electron configuration and then you have to find the element. All you need to do is add the superscripts and see what number that is, and then go to the periodic table. So we have 2, 4, 10, 11. Go to the periodic table. Number 11 is sodium. So my answer there is going to be sodium. These ones are a little more tricky when I have to draw the arrows in for my orbital diagram, making sure I'm following all 3 rules. Also, this is an ion. I have a -1 charge, meaning 1 more electron. So if fluorine has 1 more electron, it's going to have 10 electrons. It's going to look like neon, but it's still going to have its 9 protons because it is fluorine. Remember, the number of protons identifies the type of element we have. I'm going to try the drawing thing here. It kind of broke my computer last time, so hopefully it works out here. I'm going to draw in my arrows. Watch how I do it. I start at the bottom. I'm going to work my way up. Don't judge my arrows. It's really hard to draw with my mouse here. So far I have 4 electrons. How many did I say I needed? I needed 10. So I'm going to fill each of these individually first, according to Hund's rule. And I'm going to have them all have the same spin according to the Aufbau principle, or no, the Pauli exclusion principle, sorry. So far I have 2, 4, 6, 7, 8. So I need 2 more electrons there. Ooh, that one's not very good, but you get the gist, okay? So there I have my 10 electrons being represented for my fluorine. And then the electron configuration would follow suit as well. And you'll get through the pattern. The pattern doesn't change. The pattern stays the same. 1s2, 2s2, 2p6. We're just trying to figure out where those electrons are building up from the bottom to the top. So we're always starting at 1s. Hydrogen is the most simple with 1s1. Helium then being the second one with 1s2. And so it follows the pattern on that periodic table. So let's look at the we do section. Pause the video. Go ahead and try these 3 problems out before you unpause and get to the answers. I'm going to go ahead and jot in these answers for you. So sulfur, if you look at the periodic table, is number 16. So we need to draw in 16 electrons. That's a lot of arrows for me to really messily draw, but watch how I fill in my boxes. I'm starting at the bottom, following the Aufbau principle, moving up to my second energy level, filling in the sub-S sublevel before moving up to the P. I'm going to fill each individual orbital with 1 electron before moving on to the next orbital. How many electrons did I say I have? I need 16, so almost full, right? Because if all of these boxes are full, I'm going to have 18 electrons, which is the most complex that you could have. So I'm getting there. Again, filling my P sublevel individually before doubling up. So right now I have 2, 4, 6, 8, 10, 12, 13, 14, 15, and I need 16 electrons. So I need 1 of these to be doubled up. And there we go. We have our electron configuration for sulfur. So again, this one's the easiest one. I just need to count the number of electrons present, then go to the periodic table. So here I have 2, 4, 10, 11, 12, 13, 14. If I look to my periodic table, that is silicon. Big capital S, lowercase I. Potassium +1. So when I have a +1 charge, I have 1 less electron. So potassium normally has 19, but this is actually going to be 18, our max amount of electrons we can have in our electron configuration. I'm going to try typing this one out. It doesn't type like the little superscripts and stuff correctly, but I'm going to end up with 1s2, 2s2, 2p6, 3s2, 3p6. So this is the most complex electron configuration that you will potentially need to write. I'm going to put spaces because that looks really confusing otherwise. Between each of these, and if I add up the superscripts, I get my 18 electrons that I have for that potassium. So as with everything in this class, practice, practice, practice. So I do, we do, you do, your turn. Take this URL and practice the apprentice and the master sections. The other ones that are available have some trickier compounds, so you can just skip through those or guess. but 1 through 18 are the ones that you will need to know. So practice those, and then we're going to move on to 2.4.